Hi there, and welcome back to Basic Math for Economics. In this video, we're going to work on a constrained optimization problem. And I left everything general just to give us a little bit of a challenge. So anyways, let's take a look at it. In this situation, we have a consumer who needs to choose how much of goods X and Y to purchase. And they're facing the utility function of X to the alpha power times Y to the beta power, where again, alpha and beta are just positive numbers. They're just numbers. They're also going to face a budget constraint where the amount they spend on goods X and Y, which is PXX plus PYY respectively, cannot exceed their income, which I'm calling I in this case. So PXX plus PYY must be less than or greater to I. So let's figure out how much we want to purchase of good X and good Y in equilibrium in this situation. So let's set up our optimization problem. So the first thing we need to remember, of course, is what exactly we're doing. Well, we're maximizing. So we'll start with the max, and then we need our choice variables. So we're choosing X, we're choosing Y, and then once we add our constraint, we're also going to choose lambda, which of course is our Lagrange multiplier. So we're going to maximize our objective function, which of course is our utility function, which is X to the alpha power, Y to the beta power. And then we're going to add our Lagrange multiplier times our constraint. And remember that we need to rearrange our constraint such that it's greater than or equal to 0. So down here I can rearrange this. I get I minus PXX minus PYY is greater than or equal to 0. I just subtract PXX and PYY from both sides. And then I can just put that in right here. I minus PXX minus PYY. And there we go. There's my Lagrangian right here. And we are ready to calculate first order conditions. So we have three choice variables in this situation, which means we're going to need three first order conditions. One first order condition of our Lagrangian for each of these choice variables. So let's start working on them. So first let's do X. So the derivative of my Lagrangian, that's what that little funny L is right there, with respect to X. It's going to be, and we're going to use our power rule, alpha X to the alpha minus 1, Y to the beta, and then minus lambda times PX, and we'll set it equal to 0. And again, I'm just distributing the lambda through those parentheses. That's where I'm getting that variable right there. Then I'll do it again. The derivative of my Lagrangian with respect to Y is equal to beta X to the alpha, Y to the beta minus 1 minus lambda PY, and again I set that equal to 0. Need a little bit more room. And lastly, the derivative of my Lagrangian with respect to my Lagrange multiplier is just my constraint. It's I minus PXX minus PYY, and we'll set it equal to 0. And so I have three equations, three unknowns, and I need to solve this out. Which again, it can be tough, but we have tricks to simplify this analysis, and let's remember those tricks. So let's start with these first two equations right here. Let's actually rearrange them. All right, let's see if I can keep them on the screen. So I have alpha X to the alpha minus 1, Y to the beta, move the lambda PX to the other side, equals lambda PX. And then I'm going to divide it by the left-hand side of my second first order condition, beta X to the alpha minus Y times, that should just not be there. Get rid of that. Y to the beta minus 1, and divide the right-hand side by lambda PY. So basically I've rearranged my first order condition and my second first order condition, and then I've divided one by the other. The reason why I do this is because it allows me to cancel out lambda. And I can, let's scroll up a little bit more, rearrange both of these sides. I'm going to find that my left-hand side right here is alpha Y over beta X equals PX over PY. Or, rearranging this a little bit more, I get a nice tangency condition. I'm going to say that PXX times beta over alpha equals PYY. That's it right there. That's my tangency condition. And again, remember that the tangency condition is going to tell you what the slope of the utility curve has to be where our solution is going to lie. All right, So now that I have a tangency condition, I can combine that back with my budget constraint and I can get our solution. So let's write that again right here. I have I minus pxx minus pyy equals 0. Let's plug in this pyy right here. So we get I minus pxx minus beta over alpha pxx equals 0. Okay, left-hand side, I have pxx plus beta over alpha pxx, and that equals I. So right-hand side, everything without an x. Let's factor out an pxx out of the left-hand side. I'm going to get pxx times 1 plus beta over alpha equals I. This is just what? Alpha plus beta over alpha. That's all that is right there. And so now I can, let's see, divide both sides by px alpha plus beta, multiply both sides by alpha, and I get x star equals alpha I over alpha plus beta in parentheses px. And there we have it right there. So that is going to give us my equilibrium value for x, and I can go back through to my tangency condition, which is of course right back up here, and I can figure out my value for y. So I had pyy equals beta over alpha pxx. So I can plug in this value, so pyy equals beta over alpha px, and then I have alpha I over alpha plus beta px. Good news is px cancels, alpha cancels, and then divide both sides by y. I get y star equals beta I over alpha plus beta py. And that is going to let me solve out for both of my unknowns right here. I derived two demand functions, one for good x, one for good y, as a function of income, function as the price of good y, and a function of my parameters as well, alpha and beta. So this is a bit more complicated than having numbers right here, but it's still doable. The algebra is a little bit more intensive, but again, nothing we can't handle. So anyways, that's actually all for this video, and thanks for watching.